All right, everybody. I thought I would give you a quick video on how to turn DIANN results into Skyline so you can visualize the peaks. It took me too long to figure this out. There's only one part that's not documented, and I had to ask the Skyline support team, which is super, super useful. But once I worked that out, really, really easy. So we're going to need two things, really a couple things. First thing we'll need is DIANN. I am using the brand new version from the Quantum MS paper from bioRxiv. So the way to find that is you go to the full text and you scroll all the way down to the bottom, and there will be a link. Data availability. You'll see this link here starting with osf.io. We're going to open that in a new tab. And you could see the program is right here. So you download this DIANN 1.8.2 beta 22 setup. You install that. You could download some process data too if you want to use it, but we're not going to use that right now. You'll also need Skyline, so skyline.ms. We are using the Skyline beta and not the regular Skyline, but I think it works with both. I think I've tried it with both, but right now we're using the Skyline daily, so it should work with both, but I can't promise. Okay, so what you want to do is make your DIANN or Diane search. What we're searching now are two 50 nanogram HeLAs I just did as a QC sample for my new Bruker-Timstorf HT. I ended up searching them with two different libraries. Basically, it was library free, but I did one against the entire human proteome, which I converted into a spectral library, a predicted spectral library in 2 steps using Diane. And I think I have a video on this. It's a little old at this point, but it's still good. And anyway, I converted the entire uniprot FastA proteome into a predicted spectral library, and I searched that. The other one I did was a HeLA in-house, which I took a bunch of DDAs from HeLA files that I ran on my Timstorf and turned that into a smaller library. And then I queued those up in the pipeline. So the Diane pipeline is super useful. And it's really easy. You just kind of make your parameters, hit, where do you go? Add to pipeline. You can give it a name, and then you could run the entire pipeline. So it did one search after the other. Okay. So when Diane was done, it output a bunch of files. And here's the in-house one. Let's see, for the HeLA in-house one I did, it contained, let's see, we'll open the log file. I think there was about 8,000 proteins in there in the library. And this was a 50 nanogram EvoSep, 100 samples per day on the Timstorf HT. The in-house one ended up identifying around 4,220 proteins, 3,933 protein level proteins. That's pretty good for 50 nanograms, 11. I think this is 11-minute run, something like that. That was a little more sensitive than the entire human proteome, which identified about, let's see, 3,300, 3,600, depending on what numbers you want to use. High, like, low to mid 3,000. So less sensitive than the in-house, but that's what you would expect because this was the entire human proteome. So your sensitivity is going to be less. Okay. So what files do we need for Skyline? Okay. So the first thing we're going to do is open Skyline daily, and we'll just open a new one. I have a couple instances open. So we're going to open Skyline daily, and let's see, what are we going to do? We're going to go import DIA peptide search, and it takes me a couple times to get this right, but hopefully I'll get it right in this video. Okay, So you must save this document to save it. To continue, I'm going to just save it on my documents directory and call it video DIA NN test or something. Okay, we'll see if that works. All right, so for spectral library, we're going to build the spectral library. This is where you're going to run into trouble. And I had to ask the support on how to do this. But once you get it down set, it's super, super easy. And the thing is, you're going to want to feed it this Gila, 50 nanograms Gila TSV speclib file. But if you sort by name, let's see, did I do this today? That was yesterday. Let's see, did I already do this? I think. Let's see, where is, I want to make sure I do this correctly. Where is the output? I think this is right. We'll see if this works. Basically, you have to rename one of the files in your Diane output. And let's see if we get this right. We'll try it with the human proteome. And essentially what you do is you want to feed it the build library, add files, and we're going to want to give it that file we made, and I think I put it in here. Let's see, output, human proteome, and basically you give it a speclib file, and it will read it, and it'll say, give you the score threshold of 5%, that's fine, score type Q value. If what I do is I always change the IRT standards to CIRT, and I think that's important. That's what I always do, and usually it'll find the index retention times peptides from the CIRT files. And if you want to Google CIRT, it's really, really useful. It's one of my favorite papers to read. Okay, let's see if this works. And it will probably give me an error. If it doesn't, I've already fixed it, and I'll have to go back. Yes, all right. So it gives you an error. So it says unable to determine DIANN report file name for 50 nanograms. This is kind of a bug as far as I know in the library building methods. So you can ignore all this stuff it tells you, and we're going to fix it. Okay, so let's do that again. Go get new document, or we'll go start, import DIA peptide search. We're going to give it that speclib file again, timstoff HT, output, human proteome. We'll give it the speclib file. Okay, so in order not to get this error, what we're going to do is go to that directory. Let's see, output, human proteome. And basically what you need is you need a file that, let's see, starts with the same file name as the speclib, but this is the wrong one. So what I always do is I sort by file name. Here's the speclib, I fed it. Here's the output from Diane. This is not the right file. So what I do is I just change this to like old or something, because it'll look for like a TSV file. So we want to get that out of the way, or just copy it to move it to another directory. And then the report it needs is actually, let's see, which one is it? It is, is it the report first pass, or is it, it's report. Okay, so it actually wants this big file, that's report. And usually this is the second biggest file. So the biggest file is wrong. This is the report it needs. So what we do is we rename, I'm just going to copy this from this file because it has to match. And we take this report.tsv and we rename it. And we put this on top and like underscore or something, report, boom. And now it is the same name. So we have 50 nanograms HeLa.tsv.speclib, 50 nanograms HeLa.tsv underscore report. So as long as your speclib file name starts, your report starts with that same string of characters, it'll work. And remember, go back in the video and get rid of this one, change that TSV to old. And now I'm predicting it will work. So let's see. Okay, so remember to put CIRT. That's very important. I've never experimented with include ambiguous matches. You may want to do that. And then we're going to hit build and we're going to hit next. And I predict we are not going to get an error. So let's see. Oh, we did. Oh my God, what's wrong? All right, let's try again. All right, it takes me a few times. Yes, so let's try again. Import DIA peptide search. Let's see, you guys can laugh at me while I go do this because it takes me a few times. HT, output, proteome. What did I do wrong? I think I did that correctly. So that's TSV. Proteome. Did I do that right? It should have been. Let's see. Report. Oh, I did it on the wrong directory. That's what I did. Okay. So let's rename. This is the output I did. For those of you watching at home, you're probably like, you went to the wrong directory. All right, so let's open it again. And we'll redo. Let's see if I told you is correct. So the speclib file, you'll see this one. We're going to rename as old, and I used the wrong directory. That's why. So now we're working at the right directory, old. Yes, and we'll take the biggest file, this one, rename. Okay, and then we're going to rename this, and we'll put that at the beginning, underscore. Okay, why didn't that work the first time? I don't know. Let's make sure we're loading the right file in here. So add files, we're going to go to make sure we go to the right one. We'll give it, do we see that old file in there? Let's see. We should, right? Where'd it go? I don't know. Oh, it's filtering it away. Okay, so we go speclib, give it the speclib, CIRT. Okay, let's do it. Boom, and it worked. All right. All right, you just have to go to the right directory. Okay, so it found 93 distinct CRT peptides are found. How many do you want to use? I don't know, 93. You can pick 40 or 50 or 10. Why not use 93? Maybe if you do the top 20, it works better because they're more intense, maybe? I don't know. But, okay, let's do 93 and see if it works. 93, hit OK. And we see, let's see, this looks good. The R squared means that it worked correctly. You could click on the success and it'll show you these are all the CRT peptides found. You can see this is a 12-minute run, so peptides start coming out at 2, going up to around 11 minutes. Awesome. Okay. Okay. And remember, I'm going kind of fast, so you guys can rewind the video and slow down. Okay, so I hit OK. Do you want to recalibrate the IRT values relative to the peptides being added? Sure. Yes. Why would we not want to do that? I don't know. Okay. All right, updating peptides. All right, now we're going to add our results. So let's see, we go computer, I believe it was on the F drive, Brett, Timstoff, HT. These are the two 50 nanogram files. And you hit, let's see, open. We're going to import both of them at once. How many to do simultaneously? We'll hit next. I don't ever remove these. It tries to remove the first part of the file. I usually don't do that because it confuses me later. Okay, we hit OK. And then we did oxidation. Might as well click that. It's just asking you what modifications you want to add and add a variable oxidation. Okay, we hit next. I usually keep these as default. The defaults in this version of the daily are good. Pick the top 6 transition ions, minimum 6. Everything looks good. Precursors 2 and 3, ion charges 1 and 2, YB precursor. Boom. Okay. MS filtering 1, centroid, mass accuracy 10, should be fine because it's should be okay. DI acquisition method, DIA results only will work. You could change the ppm, the 10, the maybe 15 or 20 ppm. I don't know. Let's do 20. That seems about right, better. Maybe it's recalibrated, but it still has to find the peaks in the raw files. So let's do 20. That should be fine. Let's see, ion mobility filtering. It will do the ion mobility, but I don't know what the correct resolving power for the timsTOF is. So I'm going to leave that as default. If you guys know, let me know. Okay, so MS1 filtering, MS2 filtering. Good. All right, let's hit next. All right, now we'll need our FASTA file, and I believe we searched this with one miscleavage. We can go back and check. I actually named my speclib name. I also keep the log file when I predict the human proteome. So I believe I put it here. So this is just the uniprot FASTA for human, one protein per gene, so it's about 22,000. Okay, miscleavage, generate decoys. I usually do this. You don't have to. You don't have to because DIANN already filtered the results for you. But sometimes I like to include the decoys just so I'm not fooling myself. Plus, it's fun just to look at the decoys and say, hey, that decoy looks really good. So usually I do it. And we don't need to automatically train an mProfit model because it's already been done by DIANN. Well, different models, but DIANN model. Okay, so now we go finished. This should work. Okay. All right. So it's inserting the FASTA. There's going to be about 22,000 proteins. I think. No, why did it stop at 4,000? Oh, that was probably from the spec library, I think. Okay. Creating proteins and targets. This is a fun part. So this is cool. So you can't do this with Diane really easily. So we're going to create protein groups. So basically it tells you, let's see, we found 4,311 proteins. That's really good for 50 nanograms, 12 minutes. Basically this unmapped is because there's 22,000 proteins in the uniprot. So those are the ones we didn't find. 21,000 peptides. 52,000 precursors, pretty good for 12 minutes. All right, so now we're going to create protein groups because we want to create protein groups. That's best practices as far as I'm concerned. Okay. And Skyline is really good at that. Okay, so mapped. So it tells you there's 21,000 peptides. Shared peptides is 3,209. What do you want to do with these shared peptides? Duplicate them, assign them to the first protein group, assign them to the group with the most peptides, remove them. Totally up to you. We're just going to duplicate them for now, but I can see the advantage of removing them. Okay, so we're just going to duplicate them. Okay. All right, so now we have 4,104 proteins, and we're going to find the minimal set of group list that explains all peptides. Let's do that. That sounds cool. Okay, that's going to take a minute. All right, so now we have 3,000. It decreased the number of protein to 3,753 protein groups. Okay, and if you want, what's really cool is this is the easiest way to filter Diane results with more than one protein peptide per group. So let's see what that does. So we currently have 3,753 proteins. What if we want to do minimum of 2? I personally like to keep it at 1 because I have found a lot of one-hit wonders through DAA data that are really, really useful. So I would recommend keeping it at 1. You can see if we decrease it to 2, now we're down to 2,007. Increase it to 2, we're down to 2,737. I'm going to keep it at 1 just because of past experience. Oh, did I accidentally do this the wrong way? Okay, come on. Did I do this 1 or 2? 1. Okay, so now we're back up to 3,753. So in my experience, after looking at hundreds and hundreds and hundreds of data sets, maybe not hundreds and hundreds, but hundreds of data sets, I have found a lot of proteins that are identified with one peptide that turn out to be very valuable. So I usually keep them. Okay, so then I hit OK. So we got 3,753. And you may want to experiment with these to see which works best for you. I hit OK, and boom. Now it's working. Okay, so you could see it's really fast at importing the timsTOF data. It should be even faster for Orbitrap data, or maybe it's about the same. I don't know, but it's actually really pretty fast. And it should be done in a couple minutes. And you can see we have all of those 3,755 proteins here on the left. It's almost done. We can even click on them now to see the peptides for each protein. It's kind of nice. Okay. Almost done. Now, the only thing I'm unclear of is whether this keeps the peak boundaries for Diane or it makes its own peak boundaries from the spectral library. That I'm not sure. But we can import the peak boundaries from Diane. I figured out how to do that. It's not hard, but I'm not clear. I haven't tested it yet, so I'm not clear if that actually changes the peak boundaries or if it reads the peak boundaries from the spectral library. I don't think it does, but it could. Okay. All right. It is this gradually is turning kind of a greenish yellow. Okay, should be done in a little bit. Okay, so when it's done, this was human proteome. We can import the peak boundaries from Diane if you want to make sure the peak boundaries are the same. And I did this once and it worked. And you essentially have to open one of these, I think. Let's see. Okay, there is it this one? It's either this TSV file or the one we imported. Let's go ahead and open that with Notepad++. Okay, and you should see quantity, retention time, start. So there's two things here. There's retention time start and retention time stop. And we can actually open that in Excel to make that easier. Because Skyline is going to look for a different header. So retention time start, retention time stop. So I think we opened the right file. So this was the one we renamed to import into Skyline. And let's see if this works. I did it once and it worked. Let's wait till it stops here. Okay. All right, you may want to fast forward for a couple minutes. But essentially what we're going to do is once this is done, we're going to go to File, Import Peak Boundaries, and you try to import that file and it will say it is looking for a header that it's not found. It'll tell you what the header is. And essentially what you do is you go back to this file and then just rename retention time start, retention time stop, and something else. It may give you one more and then it should work. So let's see. Whether it works correctly, I don't know, but at least it imported without without an error. Okay. Let's see. Come on. I think I actually have one that's open, but I don't think I imported the results yet, so let's just wait. Feel free to fast forward. I don't know how to actually pause it on open broadcasting. It just says start and stop, but it would be nice if there was a, let's see. Okay, almost done. All right, so what else can we do while we're waiting? I think that's about it. And do I have any other ones open? Here's one from that I did from when I searched this a different way, but I did import it from Diane. And so you can see my peaks. These are the, I made 40. I made picked 40 peptides out of the 25,000 or whatever that are also CIRT peptides that span the retention time from, let's see, 2 minutes to 12 minutes. And so that way I can monitor my peak areas and retention times with panoramic QC over time. And you can see some of them look really nice, but it's kind of tailing. And let's see if I have Spectronaut open on this file, on this computer. I may not have it installed. Let's see. Come on, not calculator. Spectronaut. Let's see if I have it activated. Okay. All right, let's see if I have the viewer activated. If you don't, oh good. All right, so let's open that same result in Spectronaut. I think I have this in, let's see, lab, timsTOF, HT, initial specs. Believe I have a Spectronaut result here. Let's open it. And then what's cool is we can compare some of the peaks from Spectronaut versus Diane. You can see this is about the same, a little less. Maybe protein group's about the same, maybe. Skyline, Diane, I don't know, 3,500. Approximately. Again, not bad for 50 nanograms. And what's cool is this was a new column and I'm getting some tailing. And so you could see some of the tailing here, for example. Here's a good example. Let's see. This is from, it's a CART, so heat shock protein 76. So no, probably pretty abundant peptide out of the 25,000. So maybe this one's a little overloaded or something, but I am getting some tailing. And so you can see the peak boundaries that Skyline made. And let's just look at this under Spectronaut while we're waiting for our Skyline to finish. Okay, so the way we're going to do this, we're going to make sure we're on the same file. So this is file 78. This is file 78. So make sure we're looking at the right one. And we're going to look for the same peptide. So there's a little drop-down box. We'll go, and I think it's assay peptide sequence. We're going to type in the same peptide sequence. So VEILAL. Let's see if we have some. So that's funny, it's not in here. Let's pick one that Spectronaut finds too. It's funny it didn't find it. VEILAN. Let's see if it found. We can look for this one later. VEIL. And I don't see heat shock protein 60. So let's look for one they both found. That's interesting. Spectronaut didn't find it. How about this one? This is a nice tailing one. Let's see. Might be a reason. YR. I'm getting old, so my eyes don't work. IRPG. Maybe this is it. YRPGTLAR. Okay, this is the same one. This is a +2, so that's this one. 516.81. 516.801, 516.801. All right, let's look at it. So here's my peak in Skyline. Let's look at it under, there we go. It's the same one in Spectronaut. You can see it sees the tailing here. And the one thing I've noticed, and I've noticed this about my tailing peaks, is that Spectronaut seems to be doing well, I guess that's a better job at picking the peak boundaries here. You can see how it's a lot closer, where Skyline is really long. I don't know. We'll see if I import the Diane. I can import the Diane results and see if that changes. So that's one thing I've noticed. So, but you can go back and forth. It's actually interesting. I find it interesting to go back and forth and see the difference between the two programs. All right. Let's see here. Okay, let's see if it's done. Is it finally done? Almost. Almost. All right, what else can we find out about? Let's look through here. What else is interesting is I don't know how to read the, let's see, peak annotation, 2D spectrum. So you can see the ion mobility here. So it did import the ion mobility. So here's the 1 over K naught of 0.8 something for this peptide. I find Skyline's a little hard to read. It's hard for me to make sense out of it. Maybe I'm just not used to it. But on this one, what's really nice is you can look at the MS2 ion mobilogram. Oh, you can't do it. Let's see. I will map the raw data. Let's browse. This may take a minute. Let's see. HT. Here we go. It's right here. That's the directory. Okay, so now it finds the raw files, and then we should be able to do this again. MS1 ion mobilogram, MS2 ion mobilogram. There we go, 0.85. I find this a lot easier to read. And look how it's nice and symmetrical there. That's kind of cool. And so the predicted ion mobility is right on, predicted retention time. Right on. And we can even look at, what else can we look at? I also like to look at the peptide predicted match, which is cool. It's amazing about DIA is that it just picks this stuff right from the background, right? You totally believe it though. I believe it. Let's see, intensity correlation. Yeah, okay. Let's see if we could do retention time. I think what we can do is we go here and we can view, let's see, ion mobility calibration. So it does a good job of calibrating the ion mobility. Let's see, extraction width. Yeah, it's kind of cool. You can do a lot of stuff. Okay, is it done? I think it's finally done. Let's see. Okay, is it done? I think so. Let's move some windows around. Come on. There we go. All right. Okay, so we're going to go peptides. And let's see. View. Some of these don't look as good as others. I like to look at, let's see, transitions, all split graph. And what I like to do here, let's just move these side to side here. And so out of 25,000 peptides, some are going to look kind of sketchy and some not. But at least you can kind of see. And let's see if we can change the, import peak boundaries. So we're going to import peak boundaries. And we're going to go, let's see, output, human proteome. And we're going to try to do this report. We fed it. So I think it's that one. And it's going to give us an error. And it's going to say, oh, because it's being used by another process. That's annoying. All right, so close that one. Okay, we're gonna try that again. File, import, peak boundaries. This sort of worked the last time I did it. We're gonna give it that file, and it's gonna give us an error because it's gonna look for, let's see, new. Okay, I just kind of save that so I remember what it, min start time. So we need peptide modified sequence, file name, min start time. Okay, so we open that file again. Okay, let's see, program output, report. This was the one we renamed. Oh crap, I don't want to open it. And I want to open it in Excel. Let's see, we'll just open it in Excel. I'll drag it in there. Okay, and then what did it want again? It wanted, let's see, failed to peptide modified, oh gosh, peptide modified sequence. So I believe that would be this one. I think. So we'd want to change that to peptide modified sequence, whether it's case sensitive, I don't know. Peptide modified sequence. File name. Okay, almost. So file name, min start time, and is that a space? I think so. No, maybe. Min start time, I would say no. Let's go see min start time. I believe that's here. Min start time. Let's see if this works. Min start time. Did I do that right? And then max end time. Max end time. End time with spelled correctly. End time. Okay, let's try that. And we're going to save that as a new file. This may or may not work. And we'll put for Skyline. Okay, let's try that. All right, we're going to close it or else it'll complain again. And then we go, okay, file, import, peak boundaries, and then sort by date for Skyline. Let's see if this works. Does it work? Oh, it looks like it's working. I can't believe it. All right, so I think it's working. This is as far as I've got for importing peak boundaries. So it should, last time I tried this, it gave me an error that, what did it give me an error for? That not all the peptides were found. That's probably due because I used in contaminant database too. So you might want to take that into account. I don't know, let's see if it works. Oh, and it's going to complain because I have some decoys in here. So it'll complain about that. Let's see. And you could see out of like, a lot of these are kind of, they look ugly, but you know, do you trust your eyes or do you trust the algorithm? At this point, I don't know. I kind of trust the algorithm. Okay, let's see. And whether these are the real peaks that Diane's actually seeing, I don't know, but this is the best I've gotten so far. At least it works when I picked out, I did a smaller set. So, all right, let's see. And it should give me some sort of an error, but it should work. All right, let's see. Importing peak boundaries. Okay. And while we're doing that, let's look at the spectronaut. Posting now. Let's look at the spectronaut. And I don't know, let's pick out some Let's pick out some peaks here that we can look for. Let's see. I don't know. We can look for just randomly. Let's see, add columns. I like to add column chooser. I like to add the number of peptides, gene ID, protein description. You can move those around. Okay. I like to put this over here. Let's see if that works. We could pick something mildly abundant. I don't know. Okay. Let's look at PD. We can look. Ooh, fact complex, DNA topoisomerase, PIDA, important. How about complement C4? You can look for that. CV is pretty tight. CO4, oh, that's, why does it say cow? It's probably in my contaminant database. That's interesting. Okay, let's just pick one. SF3B1. Okay, we can do assay. Is it protein meta? I don't remember. SF3B1. SF3B1. 24 precursors. Let's pick one that looks, see, these kind of look sketchy too. Well, that doesn't look so bad. GIA data can look kind of sketchy. That looks okay. See, oh yeah, some of these you're like, wait a minute, what is it picking? All right, let's look for that one. That doesn't look so bad. Okay, so I imported, so 1,799 peptides in the peak boundaries were not recognized. Why that is, I don't know. Continue peak boundary import, ignoring these peptides. It's probably because what I would suggest, what I think, is that it's probably the modified peptides, and Skyline is looking for, like, maybe the oxidation is the nomenclature is different. That's what I think. So we're getting close. We have to fix the modification one. And I hit OK. And let's look for that peptide we opened in Spectronaut. WDQT, so we'll go find W, what is it? Can I even copy that? Copy WDQTA. Okay. WDQTA. Let's see, it's a lot. WDQTA DTPK, is that it? I think so. Let's look. Okay, yeah. All right. Boom. Okay. Oh, that's not so bad. All right, so here's what it looks like. Ooh, that's pretty. Look, so it got the ion mobility, ID. Here's the transitions. That's kind of nice. And then here, let's compare that with Spectronaut. And then here's the same one in Spectronaut. Retention 3.7 minutes, 3.7 minutes. You can see the retention time's off by a fraction of a second or something. All right, so that's cool. It worked. Awesome. And what I like to do is, let's just see. Let's see, so Y11, Y10, so it basically chose Y11, 10, 9, 8, 7, 6. That's easy. That's weird. Okay, Y11, 10, 9, 8, 7, 6. Okay, so let's see. Oh, is this the same one? Let's see. 5, 7, 8, yep. Y10, 11, 7, 6. Boom. Y, you could see Y6, 9, 10, 11, 12. Is that the same one? 11, 10, 9, 8, 7, 6. 11, 10, 9, 8, 7, 6. But you could see on Spectronaut how it's only using 6, 11, and 7 to quantify. I believe that's what these little, when they're blue like that, that means the ones they're using to quantify. And so it's not using all of these, where it looks like Spectre, where our Diane Skyline is probably using all of them. But you can see it's the same. It's kind of cool. Okay, so let's look at, yeah, awesome. Okay, it worked. Sweet. There you go. All right, we did it. So I don't know. So we're obviously close with the peak area boundaries. There's some errors there. I believe it has to do with the modification, like the oxidation or the deamidation or something. Or I didn't search deamidation, so it's probably the oxidation. So I think oxidation, we just have to make sure in that report the nomenclature is the same. And so let's see if we view spectral library. Is that the one? We look for this peptide W D Q T A. What? D Q T A. There we go. Awesome. Very cool. There's 77, 8. Gives you the retention time, ion mobility. So everything was imported correctly. That's amazing. Look at that spectra. That's amazing. Okay. All right. Awesome. Okay, that's it. That's all I know how to do. I think we're like 95% there. As soon as we get that one kind of thing worked out in the import peak boundaries, or whether that did anything, I don't know. I'm gonna have to do more experimentation. But anyway, that's what I got. Hopefully you can, I think with all this information you can do too. Just have to rewind, and it takes me a couple times, as you could see in the video, to get it correctly, but it did work. All right, so we searched Diane, put Diane output in Skyline, and we can visualize the peaks, and they look pretty similar to Spectronaut. They picked the right one, at least this example. You can go through this all day if you want to. All right, cool. All right, thanks everybody. All right, I will catch you next time.